Let's get started with that. Okay, first of all, how many of you guys are familiar with FHE? It stands for fully homomorphic encryption. Somewhat. I mean, FHE, right? Yeah. FHE, like this, it's FHE, fully homomorphic encryption. That's it. Yeah. Okay. Okay. So FHE is an idea that you can operate over encrypted data. So, for example, I give you an encryption of A. And then you can perform function FA on top of it, give me the output ciphertext, and only I can decrypt the output ciphertext. Isn't that cool? That's cool, right? Okay, so that's FHE. And I try to think about FHE is that you've got a person, right? And they have a secret. This is a secret key, and they take their value A, encrypt it using this secret, and then you get a ciphertext, which encrypts A. They send it to the server, and the server is a black box. Like, no one can see what happens inside that server. It sends it to the server. Server evaluates on top of the ciphertext. The point is that the server cannot learn what it is, like server knows what function it is evaluating, but it never learns what is going inside. So it never learns the data, right? So it takes this, evaluates F, CT-A, and it outputs another ciphertext, let's say CT-A. Oh, sorry, no, it should be CT function A, because the function has been evaluated on top of the ciphertext. And it gives me back. And I use my secret key to find what FA is. This is FHE. This is fully homomorphic encryption. Okay? And this fully homomorphic encryption comes from the fact that this function could be any arbitrary function. It does not need to be an addition or a multiplication or some other fancy operation. It could be any arbitrary function of any arbitrary depth. Okay, so you can get fancy over here. You can do anything, right? So this is fully homomorphic encryption. Okay, does that sound good? Questions? Also, feel free to jump in. Like, just shout at me whenever you feel like you have a question. Just stop me, and I'll have the liberty to stop me whenever you want. Okay, so we would be starting with something called a modulus. So let's start with the modulus. Okay, so have you ever seen something like this? This is not percentage, this is modulus in our language, in computer programs. So when I write something like this, what I'm trying to do is that I'm asking you to equate this value to remainder of when you divide 7 by 3. So when you divide 7 by 3, it is 1, right? So that's a remainder. And that's the modulus operation, right? And I usually denote this particular modulus operation with mod. I mean, it's not that fancy, it's just mod, right? Because people confuse it with integers. And the way I would like to think about this modulus operation is that you have a circle, you have a clock, right? And what you have to do is that you just need to find the remainder and tell me that as the value. So let's say on a 12-hour clock, if I am telling you it's 15, what is it? It's 3 p.m. What did I do? I divided by 12, took the remainder, and eventually I just subtracted it, but I divided by 12 and took the remainder. That's the modulus operation. And so whenever I say something modulus, that is the modulus operation. And we want something formal, right? Because we want to write papers. We want something formal because, oh my God. We want something formal, right? So we want to write papers and stuff. So usually mathematicians and cryptographers denote this as ZQ. But not Q, this is for prime. ZP. So whenever I denote something like this, it's a ring of numbers modulus p. So if this is Z7, it would be a set of all the numbers that have till 7. So 0, 1, 2, 3, 4, 5, 6, not 7. You take any value divided by 7, you would get a remainder in this. It's a set, right? This is what I usually mean by ring. Now, you can get more fancy things with this, but whenever I'm saying a ring or modulus, that's what I mean. Take the value, divide it by the value, divide by 7 or whatever p over here is, and write the remainder. And it's a set. Make sense? Now, there's something else called fields. And that's the case when this is a prime. So 7 is a prime, you will get a field. With 8, you would not get a field. It would be a ring. Make sense? Today, we would not be using field as much because turns out you don't need fields for the security. You don't need primes for the security, right? Yeah, so I just wanted to add to the fact that if this is prime, then it's a field. Why is it a field? Because I wouldn't go into the depths because, okay, so I would not go into the depths of this, but it is because each of these values have an inverse, multiplicative inverse in this particular ring, and it becomes a field. And you can have multiplicative inverse because this particular value is a prime, and turns out GCD of a prime with any value is 1. GCD is? Yes. Can you say that aloud? Yes. So it is 1. And greatest common denominator. That is, with the prime, 1, right? So when GCD is 1, turns out due to Fermat's little theorem, you can figure out multiplicative inverse of each value such that when you multiply this with, you can find, like for 3, you can find a value. When you multiply with that value, it would be 1 mod 7. Right, so that is GCD, but let's not go into that. That's getting away from the topic. Okay, so modulus is clear. Any questions? Yeah. We do. You can. It's not important for security. You don't need it for security. No, you can still use fields. Like fields, so this is rings, this is fields. So rings include fields. But in most cases when you're working in, for example, in ZK, people work with fields. So I was just making it clear that you do not necessarily need to stick with fields. Yeah. You can use Q as a prime, doesn't matter much. I'm just saying that you don't need to. It was one of the misconceptions that I had when I started working with T-FHE. So I just make sure that it's clear when I'm telling people about it. Sorry, can you say that again, please? I'll get to that. That's what I'm going to get to next. That's what I'm going to get to next.
And like from the security point of view, we can try to make the ciphertext space as large as possible.
Yes, but from efficiency point of view, you would not want to do that. And there is a trade-off between efficiency and security, which for some reason always happens to be in cryptography. Like for so we would be starting with now we know modulus. That's pretty nice, and we would be starting with something called LWE, learning with errors. And I'll just call it LWE. Right, so this stands for learning with errors. And I'm just going to write a few variables and I explain them in a while. And then I would give you the hard problem that Nitanshu was trying to mention, Nitanshu mentioned in his talk. And I will tell you why. Okay, so it will be really hard to give you a very precise intuition of why that is hard, because that would require a lot of background in lattices. and even it would be hard for me as well to cover that, and probably I'll need to go through the book again, but I'll try to sort of give you an intuition of why that is hard. Okay, so let's start. I'm going to write Q, and I usually denote this as ciphertext modulus. Modulus, ciphertext modulus. I'll write M. This is message modulus. And then I'll also write something called N. What is N? N is LWE dimension. LW dimension. That's it. Now, what I'm going to do is I'm also going to say things like I'm sampling something from ZQ uniformly. What that means is that I'm just taking random values out of ZQ. Okay? And that's it. Like, so whenever I'm saying sampling uniformly, just means that I'm taking random values from ZQ. Right? So let's start. Okay. So this Q forms ZQ. This is the ciphertext space. ZM is message space. And now I would like you to have a view that Nitanshu gave us before, that is of this. Think of every ciphertext that I mentioned, like this entire, throughout this talk, whenever I mention a ciphertext, think of it as this in a mind. This is of size ZQ. Over here, we have got the message. And here, we have a bit of error. Right? So whenever I say a ciphertext, think of it as this. You've got a message, you've got an error in your ciphertext space. Okay? Make sense? Okay. Any questions? No? Okay, cool. So we'll be starting with LWE. What is LWE? For LWE, what you need to do is that we're going to sample, I forgot to mention. Whenever I write B, think of this as a binary distribution. That means I'm going to sample from 0 and 1. 0 or 1, binary distribution. Now, this is not necessary. So I'm going to sample secret value that the user has, their secret. I'm going to sample it from this uniformly. But this is not necessary. It could be ternary or it could be uniform. But turns out in T-FHE, because of the bootstrapping operation too, no, I think it changed recently, but going to the old time. I think in new paper it is, okay, yeah, going to the old time. If you want the bootstrapping operation that Nitanshu mentioned, the fast bootstrapping operation T-FHE, to stay efficient, you should use this. Sorry? Oh, okay. Oh, okay, sorry. Did someone say? Oh, okay. Okay. If you want the bootstrapping operation in the future, like I'll explain, hopefully I'll explain the bootstrapping as well. If you want that operation to stay efficient, you would want to sample from this, not ternary. Ternary is 0, 1, minus 1. Uniform is that you just have a bound and you sample it from that bound. Okay? But for efficiency reasons, we would stick with this. We are not going to go anywhere else. For CKKS, BFE, BGB, which are the other schemes that Nitanshu mentioned, for them, we usually, for security reasons and for efficiency reasons as well, we sample from ternary. Okay? Okay, so let's move forward with this. Okay, so we got a secret, S secret, and I'm going to say that I'm going to Wait, not this. I'm going to sample randomly from Z, B. Okay? So this is this. Additionally, this is not going to be a single value, it's a vector. So I'm going to sample a vector of secret of dimension n. Right? So it's a vector. With this, I'm denoting a vector. Okay? A vector. Right? And then I'm going to sample A from ZQ of same dimension. Right? So, and this is all randomly sampling. Now I'm going to get something more complicated. Are you guys familiar with normal distribution? What is normal distribution? Okay. The bell curve, right? The bell curve. This thing is a normal distribution. The mean is 0. Standard normal distribution. The mean is 0 and it has a standard deviation, sigma. Right? I'm going to introduce another parameter here called sigma. And whenever I say I'm sampling from normal distribution, and I'll denote that as this and this, so this is normal distribution. Okay? Whenever I say I'm sampling from this, I'm randomly picking a point from here. Okay? And as you would realize, 99% of the time my point would be somewhere here. And after that, beyond that would be here. Right? But 99% of the time, I don't know, 99.999, I don't know, it would be here. Okay? It would be within this bound. Make sense? Okay. So I've got A, I've got S, and I'm going to sample E. But this time, E is a single value. It's not a vector. Okay? Now you've got S, and you've got S, you've got A, you've got E. Now the LW problem says that if you take inner product of AS and add E to this, you can never ever, oh wait, it depends, but it's really hard for you to find what S is. Pardon? This? Standard deviation. And when you want to write variance, it's square. Right? Did you guys get this? Inner product. Add the error, and it's really hard for you to find what S is. And this is LWE, and that is the LWE problem. And this is the basis of T-FHE. Okay? Make sense? Easy? It is easy, right? Like, it's just here. You just take an inner product, add an error, there you go. You got a ciphertext. But now what we've not done is that we don't have a message here. It's useless. Right? So how do we add a message? Like, we found a hard problem. This is the hard problem. I'm saying that I've added error to this. Okay, so if I would have given AS, and if I would have given you multiple samples of A with same as, like multiple values, then you can find what S is with Gaussian elimination, right? Like, solve the linear equations and you find what S is. Now I've added error. So what I'm trying to say is that use the same S and use different A's. And you add error to the values. You cannot find what S is. Okay? It's really hard. Okay? Now, we have found a hard problem. That's nice. Cryptographers get really happy when they find hard problems. Like, let's build something with this. But how do we build an encryption scheme out of this? Any suggestions? Like, I want to put in message over here. Any suggestions? Like, we want to add message over here, and when I was trying it for the first time, my thought was that, why not add a message like this, right? It's still hard. Error is still there, it's still hard. But when you add a message like this, getting back to this view, error is here because error is sampled from here, which is really small. Its standard deviation is really small, right? So the norm of error, norm is like the size of error, is really small. So it would stay over here in most of the cases with high probability. Now, if I add message over here, then it would get jumbled up with error, right? Like it just gets jumbled up with error. And the point is to throw away this error. We usually throw away this error, right? We don't need this. So that means I can never recover this message if I simply add it, right? So the strategy is that we scale the message and put it in the higher bits, right? So we scale the message with delta. And what is delta? Delta is laga, Q by P, right? So we scale this, put it in the most significant bits, and message lives here.
It should be Q by M, right?
P by Q, Q by P, right?
So you introduce M as the gate exponential.
Oh, sorry. Aha, thanks. Q by M. Makes sense? So we scale it, put in the most significant bits, and we get the value, put the message over there. Well, if you put it in the least significant bit, it will get messed up with the error, right? So you cannot recover it. Now you can put it in the middle. But why do you want to put it in the middle? Let this error accumulate till over here. So you have more things to work on, right? So for example, let's say you have two. Okay, are you guys clear with this? So I can erase this. Is that okay? And then I'll get to that. Okay. This is, let's say, one of the ciphertext, right? And this is another ciphertext. This is error over here. This is error over here. Making sense? It has message here, message 1. And this is message 2. Now when I add these two values, you would notice that the resulting ciphertext would have higher error, right? But the message would get added as well. But as I keep doing it again and again and again and again, this would keep growing, right? Which is why we want maximum amount of space between the message and the error. So we can, in fact, put it in the middle, but it is not that efficient. Like it does not make sense. You should put it in the highest bits. Now I should note that this is very specific to T-FHE. For CKKS, you actually want message to be jumbled up because you're working over real numbers and you're okay with error. Because in real numbers, up to a certain point, after that, you are okay with error. In BGV, you actually scale, you put error after the plain text space. But let's not get into that. We're okay with T-FHE. It's a friendly scheme. It's one of the schemes that I find really easy to understand, which is why message is here. Okay? Cool? And
just wanted to, some guys have joined, so we have started with the T-FHE session, and can you just give us a small intro what we are trying to do here so that everyone is on the same page?
Right. Okay. Who would want to understand LWE? Not LWE, but like in 5 minutes again. LWE? Sure? Sure? Okay. So what we're trying to do over here is we are trying to build a FHE scheme called T-FHE. T-FHE. When I say T-FHE, what do you think? FHE? Okay, so what happens in FHE is that I give you, FHE is a type of encryption scheme where I have a message, I take a secret, I encrypt my message using the secret, and now anyone can take the ciphertext, perform any function on top of the ciphertext, and the output ciphertext reveals nothing, and I get the output ciphertext and I decrypt it. The decrypted value would be function evaluated on my private input. This allows you to perform functions on encrypted data. That is fully homomorphic encryption. Okay? And T-FHE is a variant of fully homomorphic encryption called Torus FHE. Torus FHE, that's it, like Torus over FHE. And the reason why it is called Torus over FHE would become apparent if I'm able to finish the session. But it is called Torus over FHE. It does not stands for threshold FHE, which a lot of people in the space think. Okay, is that okay? Cool. And over here we're talking about the hardness problem. So in cryptography we have everything relies on a hardness problem like D-log assumption and LWE assumption, and we're talking about LWE assumption over here, learning with errors assumption, right? Cool. Okay. Yeah. Where was I? So and what is LWE? It's this. You get a vector A, you get a vector S, and you add error to it. This is LWE problem. And to add a message, you scale it by this, where this is Q by M. What is M and Q? This is ciphertext modulus, this is plain text modulus, and that's it. This is a value of two values, but the condition is that message should be much smaller than Q. Okay? Cool. Right, so do you understand this intuition that we've got message over here? Okay, so we've got message here, error here, and we add these two ciphertext. The error adds up, right? Does it make sense? Cool. And I keep on doing this, the error would keep growing, and eventually, at some point, it would leak into the message, right? And we don't want that to happen, that's bad, because we would lose our message, right? So that is the point at which you would want to perform bootstrapping. Okay? You would want to refresh the ciphertext so that the error is now to a certain fixed value, which is smaller than this threshold. Okay? Okay, so this is LWE. Now, the problem in LWE is that well, what did we do? We took an inner product of two vectors, that is size n multiplied, right? Are you guys familiar with inner product? Dada plus, okay? That's an inner product. What did we do over here? This is our size n, this is our size n, this is an n square operation, right? We don't like n square in terms of complexity, right? So we want to reduce that. So if I were to tell you, so if I were to tell you that, just 2 minutes, I'll erase this and probably that would be much clearer. So you've got A1 S plus E. This is inner product. If this is size n, this is of size n, you did n multiplications, right? If I wanted you to give me, this is message as well, this is message 1, right? Now, if I wanted you to give me n messages, like I want you to give me n messages, you would do this operations again, like n times, with different a's. That is n square, right? We didn't want this. This is bad. Like, I'm giving you, like, you can look from here. You can sort of get an intuition from here that I'm doing this entire n operation just to encrypt one message. Probably I can get something better out of this. Probably I can improve upon this, right? And this leads us to ring RLWE, and I would try to give an intuition about why ring RLWE is hard based on LWE. Okay, so what I'm going to do first is that I'm just going to outline it. Okay, so this is a matrix. This is of size n as well. This is A. This is S, and these are the rows of the matrix. This is a matrix of n by n. This is A matrix where each row is sampled uniformly from ZQ. Right? This is S. How do you perform matrix multiplication? These are simple inner products. So what did you do? You did n-square operations. So if it was, let's say, A0, A1, A2, da da da, B0, B1, this would be A0, S0 plus A1, S1, and B0, S0 plus, okay? And you had to do n-square operations, right? Now, what if I could take benefit of some structure in this case? And keep this view in mind. This is a matrix. This is a vector. To encrypt n messages, I had to do n-square operations. Now, I would introduce to you something called ring polynomials. And using that, we would see that a simple multiplication of a ring polynomial blows up into a matrix and a vector product, and you can do that particular calculation, like operation, in n log n times instead of n squared times. Okay, so stick with me. We're going to start with ring polynomials, and we'll gradually come to this.
But if you say A is a vector as well, why is it a matrix now?
It was a vector before, but now I want to encrypt n messages instead of one. So this is of dimension n. You get n message out of this, right? Okay. Well, I'll tell you a general view that what happens in most papers is that they want to improve efficiency, and we are trying to figure out the best way of improving efficiency. And turns out, in most cases, as long as you start looking into polynomials, turns out you can make things more efficient. So which is what we're going to do. We're going to ring polynomials. And ring polynomials are the types of polynomials that are introduced now. Okay? Make sense? Okay. Just let me know whenever it's getting too much, and then I'll try to do some fun stuff.
Important is this theory for someone who's building on application? Is it useful or is it good to know?
I would say it is good to know, but I don't think you need this for building an application. Yeah, as long as you understand what are the cost of each operations, like what is the cost of multiplication, like how expensive it is against comparison. Yes, so you would need to have certain you would need a mind map of how relative each operation is in terms of costs to build efficient applications. But our goal, like the people that are developing the library, our goal is to make it as efficient as possible so that you guys don't have to worry about it, or at least the developers don't have to worry about it. So if we are not able to make it easy, then it's a failure on our side. So our goal is not that, but our goal is to make it as easy as possible for everyone. So if it is not, then keep just ping me with a complaint that it's not. and I should be able to help out, hopefully. Okay, so coming to ring polynomials. What is a ring polynomial? Well, the exact term for this is something called, so we would be first thinking about, okay, so I'm making in my right now, like I am trying to come up with stuff, just 2 minutes. Okay, so I'm thinking what to introduce first, to be very clear. Okay, let's start with something called cyclotomic polynomials. Do you guys know what is cyclotomic polynomial? No? Cyclotomic polynomial is a very fancy term for something like this. Let's get a bit fancy. Okay, this is called the mth cyclotomic polynomial. Do you guys know what this is? Or probably I have not done it correctly. Probably this is complex. This is designed for complex number, right? So what is this? It's a cyclotomic polynomial is a product of primitive mth root of unity. So this is a set of primitive mth root of unity. Do you guys know what is root of unity? Well, explaining root of unity would take a bit of time, but the point is that, think of this as this. This is imaginary line. This is real numbers. And then you get roots of unity. Roots of unity are values. Like if I say when mth root of unity, I'd say that all the roots all the values, when you raise them to m, they equal to 1. So second root of unity is when I take the value, I raise to 2, it should equal 1. Right? So what is the first root of unity? Yes. Root of? No, 1. Because it should equal 1. Okay, what is root of unity? That is first root of unity. 1. Right? 1. What else is there? Like just 1. And one second root of unity is like just what do you raise to? Okay, let's not get into this. But you get the idea that you just raise to the value and it's equal to 1. Okay. Okay, I think we should. You don't need this, honestly. No, not to. So what we can do is we can skip this thing, and you don't need to understand this thing. I was just trying to check whether this would be good to introduce, but let's move on to the important thing. You don't need to understand this thing to understand T-FHE or anything else. Okay. Well, the second root of unity is -1. That is because -1 square. And there's one more, and you can keep thinking about it, but I'll tell you afterwards. What we can do now is okay. Forget this. I'm going to write. Now, the entire point of introducing this thing was that I was trying to introduce you to something called a polynomial like this. Now, this makes sense? Like, this is a polynomial, x to the power n plus 1. Now, turns out, because of some properties and theorems, because of the way the cyclotomic polynomials are structured, the mth cyclotomic polynomial is equivalent to x to the power m by 2 plus 1. Okay? See, mth cyclotomic polynomial, when you sort of calculate it in expressions, it turns out to be this. Okay? Notice that this is m by 2. That means n, which is over here, is equivalent to m by 2. Right? And this is a cyclotomic polynomial. My entire point of going through that was to introduce this. Okay. Now, when I say, well, do you guys remember modulus? Right? Turns out modulus exists for this as well. So, when I say a ring polynomial, what I'm trying to say is an integer polynomial modulus this. So, x to the power n plus 1. So, you take the integer polynomial, divide it, and write the remainder. Right? So, and this creates a ring because you can only have a set of values. As I mentioned before in the modulus, there was only set of value until certain point. This would also have a set of values from integer polynomials. Right? What are integer polynomials? All the polynomials with the coefficient as integers. Okay? So this is a ring, and when I pick a value from this, that is a ring polynomial. Right? So this is and now all these set of polynomials that are in this ring are, I usually call them ring polynomials. Okay? Cool. So I would write this down again so that it's more clear. Any questions? Shoot any questions. Like any questions. So I usually denote this ring as Zx modulus x to the power n plus 1. Okay? This is the ring where each polynomial, you just take an integer polynomial, reduce it, like divide it by x to the power n plus 1, and the remainder should be the polynomial that you want. Now, there's one more interesting thing is that, do you remember the q before? Like q, m and q, like the modulus value? It also exists over here. So instead of taking an integer polynomial, I'm going to take zq. Now this is capital. Know this, because I just want to differentiate between RLWE and LWEQ. So this is capital. Okay? So what is this polynomial? It is a polynomial with all the coefficients modulus q. You take that polynomial, divide it by x to the power n plus 1, and the resulting polynomial, that is the remainder, is your polynomial. Okay? And we usually denote this as RQ. Okay? And the same thing applies over here. We have Q as the ciphertext modulus. We have N as the dimension. But right now I'm using capital N and capital Q because I just want to differentiate between LWE and RLWE. Okay? No. I just want to differentiate in terms of notation, that's it. That could be same as well. You can use the same value for Q and N over here. But I wouldn't recommend you to do that in practice for security reasons. N for this would be much larger. Nice question. In practice, value of Q and this Q is usually taken as 2 to the power 64 or 2 to the power 32. That is because these are the word sizes of our instructions on our laptops. Like on our machines, it's 32-bit or 64-bit. So the modulus operations, we get them for free. Right? So it's much more useful for T-FHE to actually have Q as 2 to the power 64, 2 to the power 120. I don't know whether there's 128-bit machine, but like 2 to the power 64 or 2 to the power 32. Or 2 to the power 16 if you're working on a small machine, but I don't think that's useful. But okay. Okay, so we have N, we have Q. And now the RLWE problem is the same. The same structure as LWE problem. You sample A from our Q N. This is a polynomial, a single polynomial. It's not a vector. Okay, I should not have done this. NQ. This means that the degree of the polynomial is n, and we're using the modulus as q. Right? So we randomly sample, uniformly sample a polynomial from RQ, just to be clear with the notation. We're randomly sampling a polynomial from RQ. We are randomly sampling S from R and B, which is binary. So polynomial with coefficients either 0 or 1. Okay? And then we again sample error from this, which is a polynomial with coefficients sampled from Gaussian distribution. The standard normal distribution with sigma, sigma. Okay? And that's it. Like, we get this, and then we multiply these polynomials. This is RLW problem, and my claim is that if I give you this, you cannot find what S is, even if I give you A. Okay? And now let's see, why does this equate to LWE? Like, why is this equivalent to the previous problem? Why does RLWE transforms itself into LWE, and why is it useful? And we need to narrow down to this particular thing. Okay, so all of this is clear? Any questions? Clear? Okay. Okay, so let me finish this thing. Like, let me connect RLWE with LWE. Okay? So all this is clear. Okay. Now, what I'm going to do is I'm going to do simple polynomial multiplication. And you would see that that simple polynomial multiplication would turn out into something that we want. Would give you the bridge between RLWE and LWE. Okay? So, if A is a polynomial and S is a polynomial, no, let's just not take this. Let's take A, a polynomial, and B, a polynomial. I'm going to write A as the coefficients of A, the coefficients of the polynomial A. Are you guys familiar with polynomial? Okay. A4, A5, right? This is the A polynomial. The coefficients of A polynomial, I usually call them coefficient vector of A polynomial. And if you have coefficient vector of B polynomial, how would you multiply? You would first multiply this, A0, B0. Yes? So what do you want is the constant term. Like, this is the constant term for these two polynomials. What is constant term? 0th degree. So how would you get 0th degree? Like, if we were not doing modulus, if it was not modulus x to the power n plus 1, then the constant term of the resulting polynomial would only be this. But the point is, it is now modulus x to the power n plus 1. That means x to the power n is equal to minus 1. So whenever we exceed the degree greater than n, we replace x to the power n by minus 1. So when you multiply, let's take n as something. N is 8, right? So this should be A6, A7, B4, B5, B6, B7, right? Because it is modulus x to the power 8 plus 1. So this could be the only these are the polynomials, and the highest degree that you can have is 7, right? Because x, now if you want to multiply these two polynomials, the first one would be a0 b0 for the constant term, and the second one would be a1 multiplied by this, because this would be degree 1, this would be degree 7, and this would result in degree 8. But we cannot have degree 8 because x to the power n, x power 8 is equal to minus 1, right? So it would wrap around and come to the constant term. It is degree 0, but since x to the power n is equal to minus 1, it becomes negative, right? So this becomes minus a1 b7. Okay, so this, then it would be this and this, this and this, right? And then this and this, this and this, and this and this, and this and this, right? For the constant term. So this becomes this a0 b0 a1 b7 minus a2 b6, right? These are all constant terms. a3 b5 a4 b4 a5 b3 a6 b2 and minus a7 and b1. This would be constant term for the resulting polynomial, right? Now let's go to the first term. What would be the degree 1 value, right? So this would be degree 1. This would be degree 1. This and this would be degree 1 again. 7 plus 2, 9. That is modulus 8, 1. But it will wrap around. So it becomes a0 b1 plus, because it doesn't wrap around in this case, a1 b0 minus a2 b7, and then you can get the notation from here, like this, right? And so on and so forth. Is that making sense? Okay. And now I can do this for each of these values. This becomes a matrix of size n. This is a matrix of size n. And what do we get back? We get a matrix vector multiplication by just multiplying two rank polynomials. This becomes the matrix. Like this particular value blows up into a matrix because of the ring structure, because of xn plus 1. And then by just multiplying two polynomials, we were able to perform matrix vector multiplication. Now the matrix vector multiplication would have taken n square time. But turns out there's something called FFTs. Are you guys familiar with? FFTs is fast Fourier transform. You can so so using FFTs, well, specifically in our case, we would need entities, which is like generalization of FFTs over finite fields, over fields, over rings. Using that, you can multiply two polynomials, not in n squared time, but in n log n times. And that improves upon the time complexity, which is why RLWE, ring LWE is important. And that is how it relates to LWE. It's nothing else fancy. Okay? I would stop here because I wouldn't want you guys hold you guys from lunch, your pizzas. So that's it. And you can contact me anytime if you have any doubts or if you're.
I think, yeah, Jay will be around here. Nitanshu is also over here. So maybe we can take a break of 10 to 15 minutes, have some water inside you and food inside you. Then we can continue after that. Maybe Jay can talk, and we also have talks from Zama and PSE. So Enrico will be talking about how we can use ZK and FHE together for verifiable FHE after this. So yeah, the break is on. You guys can talk to Nitanshu and Jay, get your all doubts cleared about FHE.
So was it clear?
Yeah, any doubts, so
Yeah.
you can ask.
Huh? In this case, yeah, you just add the way you normally do. Just take the message per ML, add it, scale it and add it. That's it. Thanks a lot, folks. Thanks a lot for coming.
Yeah, the food is over here and the drinks are over here. So yeah, round of applause for Jay.
Thank you. Cool. Have your food.